Oh, welcome back and thank you for joining. In this lesson, we're exploring parent functions, and so far we've looked into linear functions, quadratic functions, and absolute value. Next, we are looking into the shape of the graph of the exponential function. Now, we call this an exponential function because, first of all, we have a connection between y and x. So that's what makes this a function, a relation, but more precisely, it is a function indeed. And the independent variable x is in the exponent, and that's what makes this an exponential function. Just to make a few connections, remember that when the independent variable is inside the absolute value, we call the function an absolute value function. And if the exponent is in the if the independent variable is in the exponent, we call it an exponential function. And we're going to continue this form of naming in the rest of the functions as well. So as an example, I picked out a function, exponential function with base of 2, but the base doesn't really have to be 2. So this is not the only parent exponential function. Like, for example, in absolute value function, this is the only parent. But in exponential functions, this is not the only parent because we have more variety in choosing the base. So the reason why I chose this base is because it's probably one of the simplest and easiest to work with. Now, I want to add a few things about how we select the base in general. So the base has to be a positive number, first of all. The reason why we don't want the base to be negative, let's say, for example, if we had y equals negative 2 to the power of x. And we want to treat this as a, basic exponential function. Now, I want you to imagine when we give x various values to identify or to determine the value of y, because we want to build the graph, right? If x is an even number, so if the power is even, then we're going to get a positive number as an answer. So y is going to be a positive number. But if x happens to be an odd number, and as an example here, I'm going to take an even number, let's say of positive 4, for example, or an odd number such as 3.9. There are two numbers very close to each other. So if the exponent is 3.9, which is an odd number, then the value of y will be less than 0, so it will be a negative. Now imagine having, let's say, for example, negative 2 to the power of 4, which will be a number all the way up here. Sorry, my bad. So all the way up here, so at positive 4, we're going to have the y value all the way up here. And at 3.9, which is very, very close to x equals 4, the value should go all the way down here. So the shape of the graph will be unrecognizable. There won't be a solid pattern that we can observe in this case, okay? So long story short, the base has to be positive. Now, there is another value that the base is not allowed to have, and that is a value of 1. So if the base is 1, imagine that y would be 1 to the power of x, and 1 to any power would be equal to 1. So this will turn this equation into y equals 1, which is basically a linear function, or even more precisely, this is a constant function, and the graph of it will be a horizontal line. So this does not display the features of an exponential function. So the base has to be positive, and it has to be different than 1, and absolutely no 0, because only positives are allowed. Now, what we're going to do is start graphing this function. We're giving x some negative values, a 0, and some positive values. We'll see if we're able to evaluate y. So if x equals negative 4, then y would be 2 to the power of negative 4. And by using the exponent property, a to the power of negative m is equal to 1 over a to the power of m, so we flip the number to change the base to positive, then we'll have in this case 1 over 2 to the power 4, which is equal to 1 over 16. So I didn't plot this point in here. It's a very, very, very close to the x-axis because it's very, very low. And the graph has a tiny scale. Now, next we're going to give x a value of negative 3. So 2 to the power negative 3 is 1 over 2 to the power of 3, which will make this 1 over 8. And when x equals negative 2, we'll have 2 to the power of negative 2, which will be 1 over 2 squared, and that will be equal to 1 over 4. So at x equals negative 2, the y value is a quarter. Now, when x equals negative 1, we're going to have the y value 2 to the power negative 1 equals 1 over 2 to the power 1, which is equal to 1/2. Now, here is at negative 1, we have 1/2. So far, we have these 2 points on the grid, as you can see. When x equals 0, we'll have the value of y, 2 to the power 0, would be simply equal to 1. So x0, y1. Now, when x equals 1, we'll have 2 to the power of 1 equals 2. So 1, 2. When x equals 2, then we have 2 squared equals 4. So 2, 4. And when x equals 3, we're going to have 2 to the power 3, which is 8. So 2 to the power 3, which is 8. That's 3 and 8. And lastly, we'll have when x equals 4, the value of y would be equal to 2 to the power of 4, or 16. So we will connect all these points, and that will make the shape of the graph of 2 to the power of x. So next we'll discuss the domain and the range of the function. Now, for the domain, we look at what values of x were we able to give to this equation. So we gave negatives to x. We had no problem evaluating y. We gave 0. Y was identifiable or evaluatable, and positives worked as well. So we're going to say that the domain of this function is going to be x any real number. Now, for the range of the function, if you look at all these values of y that we obtain, you see that they have one thing in common: they're all positive. So we're going to say that the values of y are any real number, and any real number because it's a solid line, but the y values will be positive. Now, when you look at the x-intercept, and this is where we want to stop, remember that x-intercept is found when y equals 0. As you can see, y is not equal to 0, no matter what the x values become. We see that the y values do get very close to 0 on this end of the graph, but they never become 0 no matter how far we continue. And the way that we explain it is that this function, 2 to the power of a negative number, and I'm going to put a negative infinity in here. If you want to actually evaluate this, make the negative infinity to positive, that will be 1 over 2 to the power of infinity. So that would be equal to, so imagine number 2 raised to the power of infinity is divided by infinity. So I want you to think of it this way. So I'm dividing 1 by a very, 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 very large number, or you can think of it this way. I have $1 and I'm sharing it with the rest of the world. Now, practically, nobody gets anything, 0, but theoretically, everybody should get something, right? Because this is an existing quantity, so we should be able to share it, right? And this is why we say that the y values will get very close to 0, but they will never become 0. So in this case, we say that no matter how small the x values become, so as x approaches negative infinity, the y values will approach 0. There will be a little bit more than 0. And to indicate this, we put a plus on top of 0 to indicate that this is a number such as 0.00000. You can add as many zeros as you want, 1. And when this happens in graphs of functions, or in when this happens into a pattern is seen in behaviors of functions, we say that the function has hit an asymptote. Now, an asymptote is actually a straight line, well, a straight asymptote. The asymptotes come in all kinds of shapes, but we only look at straight asymptotes or linear asymptotes in grade 11. So when this happens, then the function will have an asymptote, which in this case is a horizontal line. And horizontal lines that serve as asymptotes, or I want you to think of them as the walls in here, like a big wall that the function, again, you can imagine this like a river, the graphs, because graphs are changing, increasing, decreasing all the time. So think of the graph of a function as a flowing river, and as it gets close to the x-axis, It will never be able to cross it because there is a wall in here, right? And it doesn't let the river cross it. So when this happens, then we say that the function has an asymptote. The way we label the asymptotes is by their equations, and we're going to say that in this case we have a horizontal asymptote with equation y equals 0. Now, the function has an the function, because the asymptote is on the x-axis, the function does not have an x-intercept, so we're going to write for this none. And some people like to write 0 in here, meaning that there is 0 x-intercepts. But I encourage you not to use this kind of term, because when we write x-intercept equals 0, the idea that we communicate is that the x-intercept itself has a value of 0, so just write none instead. For the y-intercept, we're going to say that the graph intersects the y-axis at 1, because when x equals 0, y equals 1. There is a horizontal asymptote, and the horizontal asymptote is labeled by its equation y equals 0. And when it comes to the description of the shape, we're going to say that this is a rapidly increasing function. And you probably have heard in everyday language when we say, oh, this quantity is increasing exponentially, and we use it as a figure of speech to mean, and the meaning of it would be most of the time that, oh, okay, so it's increasing very fast, right? So next, we're going to look at the reciprocal functions. So reciprocal functions are in the form 1 over x. So in this case, we're going to say that x has been kind of reciprocated, so, or reversed. And to draw the graph of this function, we are choosing the values negative 2, negative 1, negative 0.25. So some negatives, 0, and some positives. So I've chosen these specific values for a reason. You will see when we graph the function. Now let's start graphing. So when x equals negative 2, we're going to say y will be 1 divided by negative 2, and that will make it negative 0.5. So when x equals negative 2, the y value negative 0.5. Now, when x is negative 1, then we have the value of y equal to negative 1. So negative 1, negative 1. When x equals negative 0.5, then we'll have 1 over negative 0.5. Use a calculator for this. Or think of negative 0.5 as negative 1/2. So division turns into multiplication, so that's a negative 2. So negative 0.5, negative 2. We're going to try negative 0.25. So x is negative 0.25, y value will be negative 4. Now, when x equals 0, if you try to use a calculator, then the calculator will say, sorry, I cannot go all the way down to 0. That will be undefined, which means that x equals 0 makes the function undefined. Now, I want you to think, where is x equal to 0? Where on the Cartesian plane? The x equals 0 points all lie on the y-axis. So if x never becomes 0, it means that the graph will never intersect the y-axis, and it will never have a y-intercept. Make sense? And next, we'll continue with some positive values. So 1 over 0.25, that would be equal to positive 4. So 0.25, 4. Next, we have 0.5. So 0.5 will be 2. When x equals 1, y would be equal to 1 over 1, which is 1. And when x equals 2, we're going to have y equal to 1 over 2 or 0.5. We can continue this a little bit further. So when x equals, let's say, 4, it's going to be 1 over 4. So I think that these are enough points for us to kind of draw the graph, and we can connect all these points together. Now, I want us to go back to thinking about this undefined value that we got for the y value. So when x equals 0, we said x will never become 0, which means that this straight line in here, which is the y-axis, right, will serve as a wall for the values of y for this function. So we're going to say that when the function gets close to the y-axis, Or when the x values get very close to 0, the y values will just follow along the wall but never cross it. And remember what we call this? These are what we call the asymptotes. Now, because this straight line or this asymptote is vertical, we call it vertical asymptote, for short, VA. And we label it by its equation, which is x equals 0. Now, in a similar way, we are going to reason about the values of y. Now, I want you to think, if you have 1 divided by a number, no matter how large, 1 divided by, say, x equals infinity here, right? So 1 divided by infinity is going to get very close to 0, but theoretically speaking, never will become equal to 0. So as we move towards the positive infinity, the y values will get very close to the x-axis but never cross it, which means that the x-axis is serving as an asymptote as well. And the same thing is going to happen to the other side. So if the x values become negative infinity, then 1 over negative infinity will produce a number very close to 0, slightly less than 0, that we actually indicate by a small minus here to indicate that it's negative 0.001. So you can make it as close to 0 as possible, right? And the y values will get very close to it, but will never touch it. So that means that the y values will never become 0 as well. But where on the Cartesian plane are the y values equal to 0? So all the points with y equals 0 are here. Actually, all of them that are here are actually y equals 0, which will form a solid obstacle for the graph, or an asymptote, or a wall, whatever you want to call it. And because it's horizontal, we're going to call it a horizontal asymptote, and we're going to label this horizontal asymptote by its equation, y equals 0. Now let's talk about the domain. So as you can see, the domain of this function is any real number, but the values of x cannot equal 0. So that's a restriction. Now for the range, we noticed a similar pattern. So the y values were any real number, but not equal to 0. And there is no x-intercept and no y-intercept. And I will emphasize one more time, please do not write 0 when you mean none. So just write none, because 0 is a number, and in math it means it's somewhere here on the Cartesian plane, okay? Now the vertical asymptote is at x equals 0, right here, and the horizontal asymptote at y equals 0. For the description of the function or the graph, we're going to say that this is a two-piece graph. And I want you to think, if it is a two-piece graph, like, can you draw the graph of this function without lifting the pencil? So we're going to say, well, no, because I have to draw this, and then I have to jump somewhere in here to draw the other piece. So this is also what we call a discontinuous function. So this function here is continuous, and absolute value is continuous as well. So is parabolas, so is linear functions, but the reciprocal functions are discontinuous functions. Now, not all the time, that just take it with a grain of salt, because there are actually reciprocal functions that are continuous. So but this particular parent, the reciprocal 1 over x, is indeed a discontinuous function. Now, I'm going to move on to our last function, and I think that you're going to like this a little bit better, because we are more familiar with working with such numbers. And we're going to get started with a square root function. As you can see, x is inside the square root, hence the square root function name. And we are going to give x some values to figure out the values of y. Now, when we choose the values of x, we can choose 0 because we can find the square root of 0, which is equal to 0. And we can also choose a positive 1, and that is because 1, actually square root of 1, is also easy to evaluate. That's root of 1. And I'm going to plot the points, so 1 and 1. When x equals 4, y is the square root of 4 equal to 2, and the square root of 9 equal to 3, the square root of 16 equals 4, and the square root of 25, which is equal to 5. Now, I want you to look at these numbers one more time and think, what kind of numbers did we select in here? So notice that all the numbers we select are positive, and that's because we are square rooting or even rooting the numbers, which makes sense to say that they have to be positive. Otherwise, we cannot square root them. And I also, for easiness in graphing the function, I chose x values that are perfect squares, so I can plot them more easily in here because the square roots of perfect squares are natural numbers. So here are all the points that we have obtained here from our table of values. We are going to connect them, and there goes the square root function. So it starts at 0, 0, and then it increases and goes up, increasing in values of y and values of x simultaneously. So for the domain of this function, we're going to say that the domain is any real number x, and we say this because there is so many values of x, but we want the values of x to be greater than or equal to 0. So next we're going to look at the range. So you can see that the y values are also greater than or equal to 0. Now we have an x-intercept right at 0, 0, or we can say x-intercept equals 0. And whenever the x-intercept is at 0, 0, then y-intercept will be 0 as well, right? Because they go together. And when it comes to description of this graph, then we're going to say this is actually half of a parabola, but a parabola that is not sitting up like this, but it is sideways. And we are going to explore more connections that exist between a square root and a quadratic function. So as you can see here, when x increases to infinity, the y values will also increase to infinity. That would be the end behavior of this function. It is definitely a continuous function because you can draw it without having to lift the pencil. So the rest of the lesson actually is for you to work on. I did pause the answers, so these are the answers. You can check with the answers once you have come up with some definitions on your own. I hope you found the instructions useful. Thank you for learning with me, and bye for now.